Okay, so back in chapter 7.6, we learned about mass and density and how to use some of the integration techniques that we were developing to solve things like finding the center of mass, right, of some type of planar lamina. And again, just for all intents and purposes, we can just think about that center of mass as that one point, balancing point, that you could use to balance your lamina on the, say, the tip of your pen or pencil. Now, the formula that we used back in chapter 7 looked something like this, and the notation that we use to denote density, this looks like a P, but it's I believe it's a lowercase Greek letter rho. But what we had to assume back in chapter 7 is that whatever lamina we were dealing with, that it was uniformly dense, right? The same density throughout. No matter which point you choose, it will have the same density. We now want to consider some more realistic applications where, say, at two different points on the lamina may have two different densities. Well, because of this, we're going to need a function such that if you plug in the point, it would give you back out the density at that point. And as we said, depending on the point, you may have various densities. The goal is the same. We still would like to be able to find centers of mass, etc. But the way we approach it is going to have to change. So now what you can see is we're going to, when we're defining mass, we're going to make use of these double integration techniques, right? So we're still going to be setting up our double integrals over some region. Only now notice that we have a density function as a compared to just a single density. So this is what allows us to find mass and centers of mass of planar laminas with variable densities. So no more theory. I'm not a physicist for one, so I'd better get to the mathematics as quickly as I can. But what we'd like to do is, my apologies, I'm going to erase this. I'm erasing it because I started a video and then my dog decided to start barking really loud, so I decided to start it over again. So let me read. We would like to find the mass of the triangular lamina with the following vertices. Now I'm going to go ahead and graph or regraph these vertices. So 0, 0, 0, 3, and then 1, 2, 3. So connecting my dots, this is the triangular lamina that we are seeking to find the mass of. Now, so this is how the region that's bounded in the XY coordinate system, but it says, again, we want to find the mass of that triangular lamina given that the density is as follows, 2x plus y. So there it is. So there, that 2x plus y is the density function. If you give it an x and a y, it will give you back out a density. Right? And density is normally thought of as measures the mass per unit volume. But for planar laminas, we normally think of it as mass per unit surface area, if I recall correctly. But nevertheless, let's start with the region. So we know that we're going to be setting up a double integral. And we know that the density function is what we're going to be integrating. Now, what we don't have yet is the way that we're going to set up our upper and lower bounds, nor have we chosen the order of integration, dy dx, dx dy. I don't think there's, in terms of difficulty, there's much difference between dy dx, dx dy, but I'm going to do dx dy just because the majority of the double integrals I've done so far have all been dy dx. So I'm going to perform this integration this way. So let's take a look at the geometry here. So let's start with the x, right? So x starts at 0 and stops at 2. Y starts at 0 and stops at 3. Now the reason why I like to trace this out is because I know that either the 0 to 3 is going on the outer integral, or the 0 to 2 is going on the outer integral, depending on the order of integration. Now, so since I've chosen dx dy, I'm going to be using the dy as my last round of integration, so I'm going to be going from 0 to 3 on the outer integral. Okay, now I have to think about, so we're going to be going from 0 to 3, and now let's think about the x, right? Because the idea is as we go, as you know, starting here at 0, as we start moving to the right, we want it to be, we're trying to have, we want it to be between left, we're looking left to right now, so we want it to be between here, x is 0, but notice that we can't bound it, we can't go from x is 0 to x is 2, because if you did, you would have this region, right? So we're going to have to take a second and figure out what is the equation of this line, because we need it to be to the left of this line and to the right of x is 0. So I know we're going to be starting at 0, but I don't know the equation of this line here. Well, that's fairly easy. If I have 2 points, 0, 0, and what is this point? 2, 3. If I have 2 points, then I can find a slope. And if I can find a slope, then I can use a point and a slope to find the equation, right? In other words, I'm just doing this y sub 2 minus y sub 1 is equal to m times x sub 2 minus x sub 1, right? That's all I'm doing, is I'm going to find a slope, use a point to generate that line. Well, I can save us a little bit of time. So y would end up being 3 halves x, right, or 3x over 2. But because I'm going to, you know, like just for example, I can't plug in 3 halves x here, because then my upper bound of integration would match my variable of integration, right? We can't do that. So because we're going to be integrating with respect to x first, we do need to solve this for x. So x is equal to 2y over 3. All right. So this line here is the line x is equal to 2y over 3. And we want it to be to the left of that line, but to the right of x is 0. All right. So that tells me how to bound x and y. So let me go ahead and plug everything in. So 0 to 2y over 3. Okay, and this is fairly easy integration. We'll go ahead and just start working it. So we're going to integrate with respect to x. we're going to treat y as a constant. So let me go ahead and do that first round. So 0 to 3. And that's going to end up being 2x squared over 2, or just x squared, plus yx, or xy. And then we're going to be going from 0 to 2y over 3. All right, so you know the deal. We're going to be plugging in, and we're going to be plugging in for x. Okay? So if I plug in for x, it's going to look like this. So now I'm going from 0 to 3 of, let's see here, let me go ahead and plug that in. So that's going to be, if I plug in 0, obviously that's going to 0 out. So it's just going to be 2y over 3 squared plus y times 2y over 3 dy. Okay. So let's see if I can continue here. So at this stage, so I gotta square everything, try to and then I'm gonna end up combining like terms. So so let's start with the squaring. So that's gonna be 4y squared over 9, and then once you multiply y times 2y, you're gonna have 2y squared over 3. And now the only thing I'm going to do is I'm gonna multiply this second fraction by 3 over 3, so that I can get all of this into one fraction. Okay, so when I do so, it's going to look like this, 0 to 3, and that's just going to be 10y squared over 9, and then dy. Okay, I'm going to bring the 10 over 9 out front, and then I'm going to go ahead and integrate and finish this up. So 10 over 9, I'm going to go ahead and integrate. The only thing that will be left is the y squared, so that would just be y cubed over 3. And we're going from 0 to 3. So one more round of substitution gives us a mass of 10. Okay? So although there's different densities of this triangular region, the mass we were able to find of that triangular region to be 10. Okay. So if the next thing that we want to be able to do is we want to be able to find the center of mass. And you know, again, the center of mass is going to be that point that we can use to balance, you know, balance this object on, say, the tip of your pencil. And to get there, we need to have two topics that we've covered in Calc 2, and that is moments, right? So moment of mass with respect to the x-axis, with respect to the y-axis. So the ideas are fairly similar. In fact, you remember this formula or this notation right out of chapter 7. It's just, of course, again, we're dealing with double integration, right? So we have our density function and then our distance. So in other words, this y just represents the distance to the x-axis, and this x just represents the distance to the y-axis. Okay? So let me read the example here. So what we want is we want to find the center of mass of the lamina corresponding to the parabolic region. So 0, so notice they're using y here, so 0 to 4 minus x squared. And I've highlighted this text here because I want to make sure we can understand it before we go any farther, where the density at some point is proportional to the distance between the point and the x-axis. And I can see a student getting confused when there is no need to get confused. It's not that bad. So let's just go ahead and translate that highlighted text that I have. Okay. Now, first, the word proportional. We're just going, that would mean that there's some a constant of proportionality, right? We're going to have to use, we normally use k to represent that proportional constant. Now, the distance between the point and the x-axis. So let me see if I can draw it. So here is some point here. Now, what is the distance between this point and here's the x-axis? Well, isn't the distance between the point and the x-axis, isn't that just y? Right? That's the distance. So all of that translates to just y. All right. And finally, we need to formulate our density function. So in this case, the density function that we're going to be integrating is just going to be, it's going to be the distance, the proportional distance. So it's just k times y. This is our density function. All right, so next let's go ahead and sketch the region that we're interested in. So y is equal to 4 minus x squared. Well, that x squared tells me that we're dealing with some type of parabola. And we just need to sketch the parabola. So from here, and let me do my best. Okay. And of course, it's going to be bounded from 0 to 4 minus x squared. So there's y equals 0, and this is y equals 4 minus x squared. So you can see the region here. Okay, so we are going to go ahead and find the bounds in the x direction next, and then we'll take a second and we'll consider how the symmetry of this graph can make our life a little bit easier. So obviously, if you had it all graphed out, you can see that it's going to be starting at -2 and finishing at +2. But even if you didn't have access to your graphing utilities, or just didn't graph it before starting the problem, it's quite simple. You would just take 4 minus x squared, right? So in other words, you're taking y equals 4 minus x squared, and of course you're considering when x is bounded. So by making y equal to 0 and solving for x, you would get x is equal to plus or minus 2. Okay, so either way, whether you do it analytically or just looking at the geometry, you would be able to get your points here. So, all right, so that tells me that that tells me that we're going to want to do dy dx integration, right? Because the x has the constants. So we want the -2 to +2 out here, and we're doing dy dx. Now, on the inside, we're going the bounds for y, where it's going to be going from 0, but it has to be under 4 minus x squared. Okay, so all is good except what inside the integrand needs, or integral needs to be our density function. So our density function is going to be inserted here. All right, so let's take a look at what it is that we want. So there's some point in here, right, in this region, that is our center of mass, where our balancing point, right? So the goal of this problem is to find this particular point, right? And we saw from the previous page that the center of mass can be calculated using our moments divided by our mass. Now, so you could jump right in and you could start calculating. The first thing I would always do is calculate mass, and then move to moment of mass. But again, will you follow me here? Well, we'll take a break before we finish it. How's that? Okay, because I know you're probably starting to get tired. Will you agree with me that just simply the symmetry of parabolas, we know that they are symmetric about the y-axis. So that tells me that this point that we're looking for, right, if you're going to balance this, the point that you're looking for, it has to be located on the y-axis, right? So then what we know, if the point is located on the y-axis, that the x value must be 0, right? That we know. So in other words, we already know that the center of mass is going to take place on the y-axis. So we already know that x bar, or the x coordinate for the center of mass, we already know it's 0, just from the symmetry. But even if you were to continue with the math, you would find out that it's 0 nevertheless. Okay, so what are we going to do? So we are going to, we got everything set up. So when we get back, we're going to just start this integration process. But I will see you then.